Okay, I received one homework question, and that was about question 14. So let's take a look at that one right here. We have a cube of some material floating on an oil puddle, and 72.5% of its volume is submerged. And we also know that the density of oil is 933 kilograms per cubic meter. So this is similar to the iceberg problem that we did in class, where about 90% of the iceberg is submerged. And the equation that we needed for that was right here, this relationship. So what it's saying is that the ratio of the volume underwater to the total volume of the object is equal to the ratio of the density of the object to the density of the water. Or I guess in this problem it would be the oil. So for water and ice is about 90% of the density of water, and so 90% of it gets submerged. So here we have density of the oil is 933, and 72.5% of the object is submerged, so that means its density would be 72.5% of this number. So multiply this number by this percentage, and you'll get the density of the object. So you should get an answer less than 933. All right, so that's the homework that's due later tonight. The new material for today is on hydrodynamics. So what we've been talking about up to this point is fluid statics, fluids that are not moving, they're not flowing. And so now we want to go to hydrodynamics, where the fluids are actually in motion, there's flow. And to think about that, we need to consider the flow rate. So one of the important quantities for fluids and fluid flow is the flow rate. So how much volume is moving per unit of time. And the variable we use for flow rate is Q. And we calculate it by taking the amount of volume divided by the amount of time. Now when it's a liquid, which is most of the examples we're going to look at are liquids, the fluids are incompressible, meaning they can't be squished down into smaller volumes. So whatever volume that chunk of liquid takes up, it will always take up that chunk of liquid, no matter how much you push on it. That's different than a gas, where a gas can be compressed. It can change its density. Liquids don't have that property. They keep the same density. And that allows us to think about the flow in different parts of say, a pipe. So imagine water flowing in a water pipe. The diameter of the water pipe can change, but what can't change is the flow rate. So whatever amount of volume moves over here in a unit of time has to be the same as a volume of fluid on the other side in that same unit of time. So these two blocks here would have the same volume. But in order to have the same volume, they need to be different widths. So what's changing is the shape of the volume, but not the actual volume itself. The flow rates are constant. So we have Q1 being the flow rate over here has to equal Q2, the flow rate over here. Now if we break down this flow rate into volume over time, the volume would be the area times the width. And so we have area times width, and then the time would be just, we'll leave it as time. Now that's going to be the same on both sides. And then we can identify delta x, so this width difference from here over delta t is the velocity. That's how fast this chunk of fluid is moving, which means this chunk of fluid is moving at a different speed. And the thing that relates them is their area changes. So area 1 times velocity 1 is the same as area 2 times velocity 2. And that's what preserves the continuity of flow, that the flow rate is the same everywhere. And we call this the continuity equation. So this relationship right here is the continuity equation. So let's do an example. We have water at 3 meters per second in a pipe with 10 centimeter radius. And then it flows into a narrower section where the radius is only 5 centimeters. Let's figure out how fast it's flowing in the narrower section. Get rid of this from earlier. Okay, so we have the area of the pipe is going to be the area of a circle. Oops. Which is 10 meters per second squared, and multiplied by a speed of 3 meters per second. Now, if you're worried about the units here, don't be, because this is centimeters and this is meters, so this has sort of weird units right now. That will be okay, because this is going to be equal to the area on the other side times the velocity on the other side. And what happens to the area is it goes from 10 down to 5. So what we'll do is take this value, 942.48, and divide by the area on the second side, which is pi times 5 squared, to get an answer of 12 meters per second. So we use the continuity equation. Area times velocity gives me this flow rate, and then that's equal to area times velocity on the other side, so I divide by the area on the other side, and that gives me the velocity of 12 meters per second. So on the big side of the pipe, 3 meters per second. On the small section, we have narrower section, we have faster flow at 12 meters per second. So this is like when you have a water hose and you put your thumb over the end. What you're doing is closing off part of the area, making the area that it comes out smaller. When you make the area smaller, you have to make the velocity bigger, and so the water shoots out faster to maintain the flow rate. So that describes how, what we've just gone over describes how changes to the diameter or area of the pipe change the flow speed. But there are other things that could change as well. You could have pressure differences in parts of the flow. You could have height differences in parts of the flow. And so the Bernoulli equation, or Bernoulli's equation, accounts for both of those things. So this is the full Bernoulli's equation right here. It's essentially a statement of conservation of energy. What it's saying is that the kinetic energy of the fluid plus the potential energy of the fluid plus any work done by the pressure inside the fluid has to amount in no overall change to the energy of the system. In other words, energy is conserved for the fluid. So this term right here, the 1/2 density velocity 2 squared minus velocity 1 squared, this is like your change in kinetic energy. And this density gravity y2 minus y1, this is like your change in potential energy. And this here is your pressure difference, which is related to the work done by the fluid. If you have pressure 1 pushing over here and pressure 2 pushing over here, the difference in that provides some force that's doing work either for or against the flow of the liquid. So Bernoulli's equation sort of accounts for all of those different factors at once. Now, to get a better sense of what's happening, we're going to look at 3 different scenarios where one of these terms, where each of one of these terms goes to 0. Let me go back to... All right, so in the first case, we're going to imagine constant pressure. So in Bernoulli's equation, the pressure term is 0 because it's the same on both sides. In that case, we can simplify down to this. Actually, the densities will cancel out, and the difference in the squares of the velocity are related to the height change. And so what we find here is that the speed of flow, let's say at the top end, the speed of flow is small. The bottom end, the speed of flow will be fast. It's essentially converting from potential energy to kinetic energy. Okay, when you just have the kinetic and the potential energy terms, what happens is just what you would expect. Potential converts to kinetic. Now, if you make the velocity term go to zero, so it's the same flow rate, flow speed at both ends, you could accomplish this by having a pipe that has the same diameter everywhere. And then by the continuity equation, the flow speed has to be the same everywhere because the area is also the same. So if the pipe diameter is the same everywhere, the flow speed is the same everywhere, then what's different is the pressures. Because the height is changing from this value down to this value, and that means the pressures have to change as well. So at the top side, where you have, you're up high, you actually have lower pressure, and at the bottom side, where you are low in height, you have higher pressure. Essentially, the fluid is supporting the weight of what's above it, and so down here that builds up pressure, so you'll have higher pressure on the low end compared to the high end. Okay. And now the third case is what happens if there's a constant height. So the fluid flow is not going up or down at all, but the velocity is changing and the pressure is changing between different points in the flow. Now, how are those related? So the height term is gone from the equation. This term right here goes to zero. Well, now here the difference in velocities causes a difference in pressures, and we get another inverse relationship where the velocity is smaller, you get higher pressure, where the velocity is bigger, you get lower pressure. So high pressure, low speed, low pressure, high speed. That relationship is commonly known as the Bernoulli effect. And there are lots of common applications of that we'll look at a few here, or 4 here in this case. The first example of Bernoulli effect is the lift on an airplane wing. So why does a plane lift off the ground? Well, it's because of the way that air flows around the wing, and the shape of the wing dictates that. So look at the red line here, the lower streamline. In order for air molecules to make it to the other side, they have to follow this path around the bottom, and then they have to follow the blue line, this path, around the top. The top path actually requires more distance, so this is more of a straight line path than this one. And for that reason, these air molecules have to be traveling faster. So there's faster flow speed across the top of the wing, lower flow speed across the bottom of the wing. As a result, low pressure on the top, high pressure on the bottom, and you get a lift force pushing up. The next case is very commonly seen in any sports that involve a ball, which is a lot of them. So you could say baseball, soccer, tennis, basketball, anywhere where you're making the ball spin, or at some point the ball is going to be spinning, you get a sort of deflection force, which is usually called the Magnus effect, but it's really just an example of the Bernoulli effect. And what's happening in that case is that as the ball is spinning through the flow lines, it's slowing down because it's dragging some of the air around it as it's spinning. There's friction between the ball and the air. And so that means on this side, where the ball is spinning into the flow, it's going to slow these air molecules down, causing higher pressure. And on this side, it's going to speed the air molecules up, causing low pressure. So high pressure on this side, low pressure on this side, and the ball is going to deflect this way. So that's how you would throw a curveball. Or really any baseball pitch that's spinning will have some sort of deflection as a result of this. But the faster the spin rate, the more of an effect you get. It's the same way that soccer balls can be curved into a goal by this difference in pressure due to the way it's rotating. So the ball was always going to curve in the direction that it's spinning. So if it's spinning clockwise like this, it will deflect to the right. If it was spinning counterclockwise, it would deflect to the left. All right, the next example is from nature, where prairie dogs use the Bernoulli effect to create a sort of air circulation, ventilation system for their dens. And they do that by mounding up the dirt on one side higher than they do on the other. And because of that, similar to what happens with the airplane wing, the air has to flow over and hence cover more ground in less time, so faster speed across this side than on this side. So faster speed means low pressure, and that makes this high pressure. So you could think of this like a mountain. Why is it windy on a mountain? Well, the air has to get pushed over the top of the mountain, and to maintain the flow, that air has to speed up. So it's actually sped up by the shape of the mountain. And so it's always windy on a mountain. In the case of the prairie dog den, low pressure here, high pressure here makes the air flow from one side through the other, and you get a nice circulation pattern happening, which on a hot summer day can serve as an air conditioning for their den. And then the last case is a chimney. A chimney works similar to the prairie dog's den, and again similar to this here, where the shape actually dictates the flow speed, and for the air to go up and over the roof and over the chimney, it has to speed up. And that sped up air means the top of the chimney is going to be a low pressure zone compared to the indoors, where it's a high pressure zone. So if you're wondering, why doesn't, when a fire is lit, like in a fireplace, why doesn't the smoke pour into the house? It's because the Bernoulli effect pulls the air up the chimney. There's also other additional effects here. Another important one would be temperature. As the air is heated up by the fire, hot air tends to rise, and so it's going to rise up the chimney for that reason. So there's more than one thing going on, but an important contributing factor is the Bernoulli effect. Wind speed out here lowers the pressure, so low pressure at the top, high pressure inside, pulls the air from in the house, or pulls the smoke from going into the house. Instead, it goes up the chimney and out. Okay, now let's do an example with Bernoulli's equation. Putting it all together. And this has to do with a water faucet on a second floor in a house, 10 meters above ground level, 5 meters per second. We have the water pressure of the faucet. It's 172 kilopascals. What's the pressure in the water tank located at ground level, in the water, where the water is essentially still, meaning its velocity is 0. And we're going to assume fresh water, so 1,000 kilograms per cubic meter. All right, so lots of information to use in Bernoulli's equation. Let's go back and look at it briefly. We have so the kinetic energy term, 1/2 density, difference in the velocities squared, density, gravity, difference in the height squared for the potential energy term, and then the difference in the pressures. All right. So back to the example, we have water exiting a faucet on the second floor, so let's call that 0.2, and then ground level will be 0.1. So we have 1/2 times the density of water times the difference between the velocities squared. And V2 is the velocity at the faucet, and that is 5 meters per second. So V2 would be 5, and then we square it. And V1 is 0 squared, because we're assuming that at the ground level, where the water is coming from, is essentially still. So it's just moving so slowly at that point that we can call it 0. Plus, now we need to add in the potential energy. Again, we have density times gravity times now the height difference. And what we're told is that it's 10 meters above ground level. So 0.2 is at 10 meters, 2.1 is at 0 meters. So far, we've got kinetic energy in there, potential energy in there, and then the last thing we need is the pressure difference. So at the faucet, it's measured 172 kilopascals. 172,000 pascals. And then we would subtract P1. And that has to equal 0. So that would be all of the things that go into Bernoulli's equation put into Bernoulli's equation. All right, so we want to solve for P1, which is actually pretty easy. All we have to do is add P1 to both sides. And all of this over here will equal P1. So let me just delete that, and Desmos should calculate it. Oops. Should calculate it. 282,500. So our answer, what is the pressure in the water tank at ground level? The answer is 282,500 pascals, or 282.5 kilopascals, if you want to convert it back to the kilopascal units. All right, so that's essentially how you use Bernoulli's equation when you have contributions from each of the three different terms. Plug in the velocities, plug in the height differences, and then look at the pressure difference, and then solve for the unknown. In all of these problems, one of these different values will be the unknown. So let's finish with one more example, and then we will pick up with this again on Wednesday. All right, so the last example here is called Torricelli's experiment. And in the classic Torricelli's experiment, you have a container of water or something, some liquid, and then you puncture a hole at some depth below the surface. The deeper that hole is, the farther and faster the water will shoot out. So if you put the hole pretty close to the top, you get sort of a little small arc of water coming out. If you put the hole near the bottom, you get a lot of water shooting out much farther. So we're going to take the case, a hole is 20.1 centimeters below the surface. The hole has a diameter of 0.7 centimeters, and we can assume that the flow speed at the top is 0. Again, like the previous example, because it's so much slower than the flow speed down at the bottom. And then both the top and the bottom are exposed to an ambient air pressure of 1 atm. So the pressures are at the top and the bottom are the same. Okay, so if I'm plugging back into this relationship, this is going to be a 0. The pressure term is going to be a 0. The pressures are the same in both places. What else can I plug in? Well, it's 20.1 centimeters below the surface. So if I say the bottom is my 0.1 and the top is 0.2, then this difference here would be 0.201 meters. That's a difference of 20.1 centimeters from bottom to top. And then the flow speed at the top is 0. So we have a 0 squared there and a V1 squared somewhere else. And this whole thing has to equal 0. So I've plugged in everything we know into Bernoulli's equation, and you can already see that there's only one unknown, and that's the velocity. Let's come back to the question and see what it's actually asking us to do. First, calculate the flow speed from the hole. So that's this value, V1, right here. So let's do that. V1 is going to be negative, so let's bring this to the other side. And so on one side we'll have 1,000 times 9.8 times 0.201. So that's the potential energy. I'm leaving it as is. And that's going to equal 1/2 times 1000 times V1 squared, like this. So in order to get the answer, I'm going to take all of this stuff and multiply by 2, divide by, let me do it all. This way so it'll look better. Divide by 1000, and that would be equal to V squared. So to get V, I take the square root of this whole thing. So that was square root. Oops, wrong place. Okay, we'll do that again. Okay, so we find an answer of 1.98, or about 2 meters per second. Let's see. From the top, where it's barely moving, it's almost 0 meters per second, down to the bottom, where it's coming out of the hole at about 2 meters per second. Now, what is the volume flow rate from the hole? Volume flow rate is going to be area times velocity, and for the area, we'll need that the diameter of the hole is 0.7 centimeters. So 0.7 divided by 2 gives me the radius of 0.35 centimeters. Okay, so the area, let's put the area into square meters. So we want pi oh, now I know what was wrong with square root. I had caps lock on. Okay, pi times the radius, and now this is 0.35 centimeters, so let's make it meters, divide by 100 squared. So we get a really tiny number for the area, but remember, this is the area of a hole in the bottom of a container, a small hole. So we're not surprised that it's that small. But volume flow rate is area times velocity, and the velocity we calculated earlier was 1.98, let's round 5. So we get a volume flow rate of 0.000076 meters cubed, cubic meters per second. But it says convert to liters per second using 1 cubic meter is 1,000 liters. So to convert to liters per second, we will multiply this value by 1,000, which will give us a slightly bigger answer, and we get a volume flow rate of 0.076 liters per second. Okay. What is the last part? How long would it take to fill a 1 liter container with water flowing from the hole? So this is the flow rate, liters per second, times a certain number of seconds is going to get you to the 1 liter value. So what I really want is 1 divided by this number, and we find about 13 seconds. So it'll take about 13 seconds to fill up a 1 liter bottle. So let's see, what are we thinking about here? 20.1 centimeters. So imagine taking like a 2 liter bottle of soda. That's roughly this size. Poke a small hole in the bottom, 0.7 centimeter diameter hole, so about the size of like a pen or something like that, maybe a little thinner than that. But a small hole at the bottom, you could fill up a 1 liter container in about 13 seconds. So those numbers seem pretty reasonable. And we found it by using Bernoulli's equation and the continuity equation at different points in that problem. Okay, I have one more example on Bernoulli's equation, but I'm going to save it to start class on Wednesday. So that is it for right now.